So today we're going to be learning about work as it applies to the energy bar charts and what the definition of work is in physical science. So we need to take a look at a system first and then make a decision about what's going on in the system. So in this case, we are told that a spring is pushing a car from rest. And I'm telling you that only the car is the system. This is different than before, in which case I would have said that the car and the spring are the system. So we need to really focus on what the car is doing. So initially, at position A, the velocity is equal to 0, and at position B, the final velocity is greater than 0. If we were to draw an energy bar chart to represent that, the car initially had no energy, and here's my system. And finally, in the final at position B, the car had only kinetic energy. So what's going on here? Why are we representing it this way? Or more specifically, a better question to ask us is, where did the car's energy come from? So the answer to that question, hopefully you'll be able to identify, is it came from the spring. So the spring transferred its energy to the car. Okay, so I'm going to go here and I'm going to redraw the energy bar chart to represent that. So we have a car. We already said that the car has kinetic energy only at the at position B, and in position A there was no energy. So we're going to represent that by drawing an arrow that's roughly as big as the energy of the car. So now we have to label that arrow, and we need to tell the world that that arrow is the energy from the spring. So when I go to write my my equation here for this particular scenario, I'm going to start with 0 initial energy plus the energy of the spring, which I'm going to refer to as work, and I'm going to explain that in a little bit more detail in a second, is equal to the kinetic energy of the car. All right, so now we have to do a little bit of writing, so we have to do a little bit of work. So we should remember that the first law of thermodynamics the first law of thermodynamics states that within a system the amount of energy remains constant or the same. We also have to remember that energy is neither created nor destroyed. So if work is involved, if energy is entering or leaving a system, work is done. So that's the definition of work: energy leaving or entering a system. A couple of things that we should be aware of are, so if work is involved, we will use an arrow to represent that work is either going into or out of the system. And we will also label that arrow as to explain where the energy came from or is going to. In your energy equations, work will be added or subtracted from the initial energy only. We are not going to add work to the final energy because the work is really only done by adding or taking away from the initial energy. So this is the same example from before, but I'm just kind of putting it all together on one slide so we can see it. So if the car is the system, we have kinetic energy, we have work being done, by the spring. And so when we write the energy equation, we would say that zero initial energy plus work of the spring equals all of the kinetic energy that the car has. Okay, so we're going to go through a couple more examples and see if they apply here. So if we have a moving car rolling to a stop when friction is happening, or when friction is being applied, and I tell you that the car is the system, initially we have a velocity greater than zero, and finally we have no velocity. So we're going to go ahead and see what happens when we draw a bar chart for that. So in this case, we're not told how the car got started, and it kind of doesn't matter. The car is already going, so it's got a bunch of kinetic energy. And the car is our system. And it rolls to a stop. And what stopped it? Well, the thing that stopped it was friction, and friction came from the ground. So that tells me that the car was transferring energy to the ground. So we have work. So in this case, when I write my energy, and also there's no energy at at position B because the car stopped. So when we write our energy equation, we're going to have kinetic energy minus work, in this case, the ground, equals zero final energy. So that's not so bad. So now we'll take a look at another example, in which case we have a spring launching a car uphill. We're going to ignore friction, and we're going to say that our car is our system. So we have an initial velocity of zero, and we have an initial velocity equal to zero, and we have a final velocity greater than zero. And we are not going to take the spring into consideration here. Back here, I note that there's no energy here with the car, and all of the energy is with the car moving at position B. So when I draw my energy bar chart, so I have no energy to begin with, and at position B I have the car moving. So in this particular case, because it's still moving, I'm going to represent that it has some kinetic energy, and it did change position. It went up higher. It didn't go completely up higher, but we do have some gravity that we have to account for. So how did the car get moving? Well, we're going to remember that something gave it the energy, and the thing that gave it the energy in this example was the spring. So when I go to write my energy equation here, initially I had no energy, plus the work of the spring will give me kinetic energy and gravitational energy. So that's my equation for this particular example. So now we have a very similar scenario, except this time, let's see where are we at here. This time the car is the system still. We have a velocity equal to zero, and we have a position B, and at position A, and at position B we have a car that has stopped, so it also has a velocity equal to zero. So we need to figure out what's happened here. So no energy, but there's no velocity energy, so there's no kinetic energy, but what energy is present here? And we would say that gravitational energy is definitely present here. So we're going to take a look at how it affects this particular scenario. So here we have a car. That's our system. We had no energy at the beginning, and at the end the car is stopped, so it doesn't have kinetic energy, but it does have a lot of gravitational energy. So we have that. So how did the car get from position A to position B? Well, we're telling you that the spring launches the car, so the spring transferred some energy to the car to get it to its position on the hill. So in this case, my energy equation is zero initial energy plus the work of the spring equals all of the gravitational energy. Okay. Okay, so now I have another example in which case the spring is the system and the car is going to be something that we're not concerned about. So in this case, because the spring is the system, I'm only focusing on here on the spring, and the car actually doesn't matter. So in this particular case, we would say that we have spring energy initially, okay? And after the spring launches, the spring is going to be relaxed, so the spring is going to have no energy. So as an example, I'm going to say that I have all of the spring energy in my system, and once the car has been launched, the spring no longer has energy. So where did the spring put its energy? Well, the spring transferred its energy to the car. So this time, the spring did work on the car. So because the spring was a system, we focused solely on what it was doing to the car. So now this time, the energy equation is going to be slightly different. We have spring energy. We're going to subtract the work it did on the car, and that will give us 0 final energy, because we're only focusing on the spring. Now, the last one I want to talk about really briefly is a diver running off a cliff. Finally, just before he makes impact, or about to, as we talked about yesterday, make impact with the water. So only the diver is a system. So it appears that the diver has kinetic energy here, but he's up, so he probably also has gravitational energy. And since he's about to hit the bottom here, it appears that he has kinetic energy only, because that was what that statement told us yesterday. So in this particular case, is he transferring energy anywhere, or is any energy being transferred to the diver? The answer is no in this case. So when we go to draw our bar chart this time, I'm going to have kinetic energy and some gravitational energy, and at the end I have just kinetic energy. So in this case, there's no transfer of energy into or out of the system, so there is no work being done here on the diver. So that tells me that when I write my equation, I'm going to have kinetic energy plus gravitational energy will equal kinetic energy. Oops. Okay. So your homework tonight is to complete worksheet number 4, which is about work. I believe there's 6 or 7 problems on it, and we will go through that in class tomorrow.